Okay, in this video, let us discuss about the construction of an inductor. We are not going to get into uh, details, a lot of details, but just let us look at a few simple things. So it was Ampere, the scientist Ampere, who found out that if there is a current that is flowing in a wire, it creates a magnetic field around it. I think there is a right hand rule. If the thumb points towards the direction of the flow of the current, the conventional current, then the fingers basically the way they wrap around that inductor, that piece of wire is basically how the magnetic field lines are pointed. So basically they wrap from beneath it and come up in this fashion. So if the tip of this ball point, the pointer, is the direction in which the current is flowing, the magnetic lines of forces is a way that we represent magnetic field with, will be wrapped around the wire in this fashion. So basically, it will be wrapped like this. It will come out from this side, and they will be directed this way. So underneath the wire, they will basically be going to that side, and above the wire, they will be coming to this side, and a magnetic field will be established. Lines of forces is a way that magnetic fields or fields are represented, and basically, the closer we are to the wire, the the larger will be the field strength, and the further away that we are, the weaker will be the field. And we draw this by drawing lines of forces closer to each other to indicate that it is a strong field, and as we move away, we space we space more and more between the lines of forces to indicate that the field gets weaker and weaker. So this text has not come out of the blue. Basically, I had to pause the video for Azan to complete. Basically, the scientist Ampere found that the current carrying conductor creates a magnetic field around it, and he found that the magnetic field linearly relates to the current that produces it. Okay, and other scientists like Faraday and Henry, they basically worked on this further and found that a changing magnetic field induces a voltage in a circuit. So if there is a magnetic field, if we now in this magnetic field place a circuit and somehow make this magnetic field to change, how can we do that? By changing the current, because magnetic field is linearly related to the current that is causing it. So if we have another wire in here, so another wire placed, then a magnetic field that is relating is basically linking to this wire. If that magnetic field is changing, and they found basically that a voltage gets induced on its terminals. So that was a very interesting discovery, which later led to the making of generators and motors, which have basically changed our lives. We have motors everywhere around us, in the ACs, our homes, the fans in our homes, and obviously now the electric vehicles are all based on these motors, which have basically been polished and refined. But this is a discussion at very crude level. Uh, so if we have a wire in a magnetic field and the magnetic field is changing, then a voltage will get induced across this wire. So this is a subject of a later topic that we are not going to study in this course, but in the next course, the electrical network analysis. But here we are going to focus at another phenomena that couples this. If we have a magnetic field, then that magnetic field, the changing magnetic field, will cause a voltage to appear across the wire itself. Now that's something strange. Why? Because um, we don't see that a simple straight wire is going to have a voltage across it, because in our ideal world a wire without a resistance cannot have a voltage across it. So basically we are not saying that a wire with zero resistance between its terminals can have a voltage. We know that the voltage between these 2 points is zero. Why? Because R is zero. Why? Because V is equal to IR. So R is zero. Whatever the current is, V is going to be zero. We already know this thing from Ohm's law, but we are going to stick to that. However, they found that if we weave the inductor in a coil shape in such a fashion. So you see, I am trying to draw a 3D model actually, and I believe I am not being very good with it. But I hope you can have a sense of what I have tried to make. It's actually, I should have drawn it a bit like this, basically. So ignore this coil. It is just like this. So let this be a repetition of this. So you can see the wire, the straight wire has actually now been wound in a helix, in a coil, in a solenoid. And in this fashion, we have this part of the wire basically is up, and when it curls, it goes under it and comes up again. So we have actually a coil here, a coil like this. It goes down, it comes up, it goes down, it comes up. We have a coil here. So in this, it is still a wire, so it has zero resistance. So if now we have a current that flows inside, obviously based on Ampere's finding, there will be magnetic field around these coils. So for example, there is current flowing here. There is current flowing in the upward parts. There is current flowing in this direction, and in the downward parts, the current is flowing in the opposite direction. In the upward parts, current is flowing downward, and in the downward parts the current is flowing upward. So according to the right hand rule that I've used to draw the magnetic lines of forces, we can now see that the lines of forces here would basically curl this way. They will go inside and they will come up here, and in this part, for this part, they will curl like this. They will come out here and go inside in this fashion. So you see, uh, in the upward part it goes down inside in the solenoid, in the within the helix. So and here it is also the same behavior. So wherever we plot the direction of the magnetic field, we are going to see that these magnetic lines of forces, because of this part of the coil and this part of the coil, are basically adding and going inside. So inside they are going to strengthen. So we are going to have a magnetic field that flows like this across the whole inductor. So here it's going downward, inside the coil, inside the coil, inside the coil, and here it is coming outside, and then all the lines of forces, field lines, basically close upon themselves. And similarly, we are going to have lines of forces like this. So it will be a very strong field on the inside and a weak field as we move away from the inductor. So if this current that is flowing into this coil now, if this current is not constant, if we have a constant current, then basically uh, the experimenters found that for a constant current, let me write it by capital. So if the current is a constant value, then the voltage across this coil was zero, was found to be zero. However, when they change this, so I is not constant, it's a function of time, it's varying. So they found that the voltage across the terminals is proportional to the time rate of this current. And this is something interesting because although it is still a wire with zero resistance, we have now voltage across it. So a straight wire is not going to have voltage across it because the inductance aspect, or this experience, we can say, is does not happen here for the case of a straight wire. So a wire is not a good actually construction that allows this phenomenon to take place, that a changing magnetic field induces a voltage. So we are not talking about another circuit. We are talking of the circuit that itself is creating the magnetic field. The if you read the book, basically they have a very shabby and a bad explanation uh, before writing this expression that V is equal to L di by dt. Although this is what we are studying right now, but they discussed that Henry and Faraday basically studied and experimented with changing magnetic fields, and they discovered that the neighboring circuits get a voltage across it. But this is not a talk of the neighboring circuit. It is the talk of that circuit itself that is creating the magnetic field. So let me discuss that again. A current flowing through a wire creates a magnetic field around it. And if that wire is woven in a coil form, in a solenoid form, in a helix form, or a spring form, you can say, then we are going to get a structure where the magnetic lines of forces flow inside and come out, and it gets strengthened on the inside and weakens on the outside. And now you can see that the changing magnetic field links to itself. So when we say a changing magnetic field induces voltage in the neighboring circuit, that changing magnetic field is going to induce a voltage in itself as well. So while we have a current that is changing with time, that is going to create a magnetic field that is going to change with time. So when the current value gets low, we have a low strength magnetic field. But when it gets higher, we get a more strong or stronger magnetic field. So basically the magnetic field is changing. Now that changing magnetic field is linking the inductor itself. So that changing magnetic field, irrespective of this fact that it is itself creating the magnetic field, it is going to induce a voltage on its terminals. It's going to induce a voltage on each of the coil, you can say, and that is going to be added up to get a voltage across its terminal. So basically this coil like structure can be thought of a new element that is known as an inductor. And when we don't coil up the wire, it is just a conductor as we know it in circuits. And this is how we are going to draw an inductor. The symbol for inductor are coils drawn like this. But in reality, there are two ways in which we can draw this coil, but we will get to this later on. For now, you should understand that this L is known as inductance. Although the book have not used it, it is actually known as self-inductance. This term is actually used when we are going to study what happens to that neighboring circuit. So this is creating magnetic field, but it is the voltage is being induced in another circuit as well. So if we have a coil, and this circuit is what is creating the magnetic field, and we have another coil in a neighboring circuit of a neighboring circuit here, then we are going to get a voltage induced here. But the magnetic field is being created by this coil, and it's linking this one, and the proportionality, this voltage is going to be proportional to the rate of change of this current, and the proportionality constant there is going to be called M. that is known as mutual inductance. To differentiate this thing, whether the voltage is induced in the same circuit or the voltage is induced in a neighboring circuit, we use these words self and mutual to differentiate between them. Right now we are studying self inductance, where the inductor that is creating the magnetic field is the one that is experiencing a voltage across it. Remember this very important thing. Why I am emphasizing and re-emphasizing this again and again is because this is still a conductor. It has zero resistance. There should be no voltage across it. So from where this voltage comes, this is the magic of this coil like structure. We are going to get magnetic field created, and that magnetic field linking with the coil itself is going to experience a voltage induced on its terminal. This is called this the phenomena is called self inductance, and this proportionality constant is actually called self inductance as well. So this should be very simple. Okay, no, let me come to that point that I skipped earlier on. So in this symbol, basically, it's not clear how the inductor is woven. Although I believe that we are going to touch this topic later on, but let me get a hint to the very inquisitive. So let me now come up with a better drawing. So suppose we have the conductor woven like this. Can you now see the in what fashion is this woven? So it is woven in this way that if we have a current flowing downward in this conductor, uh, these parts are those that are nearer to me, and that part is which is away from me. So it is actually a coil. It is actually a coil that has been woven like this: upward, downward, upward, downward, upward, downward. So this part is the upward part, and we have current flowing in this fashion, and in the downward part we have the current in opposite direction. And that is how, basically, using the right hand rule and the upward part, we can see that the lines of forces are going to go inside and come out from the outside, and the magnetic lines of forces in each on each side are going to be like this. There is a magnetic field that basically the magnetic lines of forces point downward inside the inductor. But now look at this construction. It is still the same conductor, but now we have the coiled, the conductor coiled in another direction. So you can see it is still a downward current. So we have an inductor with a downward current, we have an inductor with a downward current, but here the part that is out of the page towards me has currents in this direction. Here it was from right to left, here it is from left to right, and in the downward part it is flowing in the opposite direction. So here, according to the right hand rule, can you see that the lines of forces are not going down on the inside, but instead in the inside the lines of forces will be coming up and going down here. So can you see, by just merely this, the way the inductors will be created, the magnetic lines of forces direction change, and that is going to change how the voltage appears across the terminals. So either it appears this way or it appears in this way. Basically it depends on this thing. But for our case, in the case of self inductance, we always, using passive sign convention, assume that the inductor is such woven that if we have a positive current flowing into the inductor and is going to get a voltage in this with this polarity, and the relation between this voltage and the positive current is going to be this way. And if the passive sign convention is not being fulfilled, and we say the current is going in here, and we have a voltage in this fashion, then in this case, this V is equal to minus L di by dt. And you can see the minus has appeared just because passive sign convention has not been fulfilled. So passive sign convention not fulfilled, passive sign convention fulfilled. So lucky for us that for the case of circuit analysis, we now have three elements, and in each of the elements, the passive sign convention holds. So for the case of a resistor, the voltage across it and the current through it are related by V is equal to IR. For the case of a capacitor, the current through the capacitor is related by this expression. Current and voltage are related by this expression. And for the case of an inductor, the voltage across the inductor is related to the current through it by this expression. And the good thing is that passive sign convention holds for each of them. If passive sign convention does not hold, we are going to put a sign on one side of the equation, and that is going to keep things very simple for us. A few small points basically related to this inductance, that because we are discussing the construction of the inductor, we can see that as the number of coils of an inductor increases, so if we have an inductor with one coil only, this and another inductor with several coils, this way we can very easily guess that the inductance of this coil is going to be higher. So basically we can say that we can therefore deduce that inductance is proportional to the number of turns. Now another thing is, if the increasing the number of turn increases two things. One, the magnetic field intensifies because of the inclusion of another coil, and the second thing is the linkage is also basically increases, due to which a voltage appears across the inductor on a whole. So we can say that the voltage that appears across this inductor, basically the voltage that appears here and here, is basically sum of all these voltages across each coil. So if we add another coil here, this voltage is going to increase. So the flux linkage is going to increase, the magnetic field strength is going to increase as well. So basically and empirically it has been found that the inductance is proportional to the square of the number of turns, number of coils, number of turns actually is how we refer to this. So N is number of turns. And you can easily sense that if we have a coil that has a small turn and a coil that has a large turn, we are going to experience a larger inductance for this case. So if the area of this coil, the cross-sectional area of the helix, then we see that inductance is proportional to the area, the cross-sectional area of the solenoid or the helix. And um, if we have and the last thing is the length. So suppose we have this equal number of turns, and we have one of the inductor like this and the other inductor is like this. We have the same area. Suppose this is the same area cross-sectional area of the helix as this one, but here the number of turns are 3, here the number of turns are 3 as well. Obviously we can see that the longer the inductor, the longer the length, the lesser will be the inductance. So we can say that the inductance is inversely proportional to the length of the helix. So let me write it with small l. So combining all these as the parameters that define the construction, L is proportional to n square into A over small l, the length of the helix. And the proportionality constant here is known as mu, and mu is called the permeability. Mu is the permeability permeability of the material that is inside the coil. Inside the coil, or in other words we can say is the permeability of the material around which the coil has been woven or made. The permeability of free space is known as mu naught and is taken to be 4 pi into 10 raised to the power minus 7 henries per meter. So this is the permeability of free space or air. They are very close. And for other materials, this may be different. So when we want to squeeze the size of an inductor to a smaller volume, basically we use materials whose permeability are much larger than the permeability of space. And in real life, the you can come across inductors in several shapes. The most common use of inductors, or where you come across these coils, are in transformers. So if you have seen small transformers, you would have noticed the winding on several legs of that transformer. That basically a winding across something creates an inductor. Pi into 10 raised to the power minus 7 henries per meter. So this is the permeability of free space or air. They are very close. And for other materials, this may be different. So when we want to squeeze the size of an inductor to a smaller volume, basically we use materials whose permeability are much larger than the permeability of space. And in real life, you can come across inductors in several shapes. The most common use of inductors, or where you come across these coils, are in transformers. So if you have seen small transformers, you would have noticed the winding on several legs of that transformer. That basically a winding across something creates an inductor.